Hi, welcome to video covering section 9.6. Didn't have enough time for this last video. So in this video, I'd like to demonstrate how you go about calculating moments of inertia. What I have here, so because we have a whole video going over this, I have a harder problem than what Shankar does, but it reduces down to one of the results that we went over in a certain special case. Right? So let me just, I'm going to jump into this problem right here. So we want to calculate the moment of inertia for a disk, a solid disk of radius r and total mass m. But the mass isn't necessarily uniformly distributed. So to keep track of how the mass is distributed, we have this function called the surface mass density. So because mass is spread out over 2 dimensions, we talk about the mass per unit area. You may also see letters like lambda, that's mass per unit length. We have sigma for mass per unit area, and then rho is normally used for mass per unit volume. Okay, so this just depends on what number of dimensions you're working in. So for this problem we're going to work with sigma, mass per unit area. And sigma would be constant. So like if n is 0 right here, r to the 0 is 1. And so the surface mass density would be constant. So what that means is that for the amount of area the amount of mass is proportional to the amount of area. So the more area I consider, the more mass is in there. So in other words, it doesn't matter if I look at a little piece of area there or a little piece of area out here, it's the same amount of mass. This problem is actually saying that that doesn't have to be the case. So if n is positive, the mass density increases as you go farther out. So like if n was positive, then more mass would be, so if you split this disk up into 2 pieces, one on the outer rim of some area and then the inner area. So imagine the areas of those two were the same. The outer one, even though it's the same area as the inner one, would have more mass because of the way the mass is distributed. Okay, so the surface mass density is a way of keeping track of where the mass is. Okay, so we're going to do this more general problem, and then we should be able to double check. So this was in our table from the last video, that for a cylinder, a solid cylinder, which is the same thing as if all that mass were flattened onto a plane perpendicular to the axis of symmetry. The moment of inertia is 1/2 mr squared. So we'll see how that arises. Okay, so the way to go about this, okay, so we want to calculate the moment of inertia of our disk. And so we're just going to do our formula right away. This is the sum of r squareds times the masses over the whole disk, over the solid disk. Okay, this is true. Even though it's true, it's not really helpful because the r, so if you split the disk up into a bunch of little pieces dm, the r is different for every piece. So it's not like this is a constant that we can take out of the integral. You can't do that. But then again, then we wouldn't know really what to do with this. You can't just say that this is r squared times m because all the mass isn't at the edge. So we're kind of stuck here. So you should think of sigma as not really being this annoying thing right here, but it's a useful tool to turn dm into something you can actually integrate over. Okay, so I'm going to rewrite sigma as dm equals sigma times dA. Okay, so see, all I did was I took this and I multiplied both sides by dA. And then sigma is also equal to a times r to the n dA. So dm is equal to ar to the n dA. Maybe that constant is, sorry, I'm going to call this constant something else. Just because a means area here, so I don't want the constant to be the same symbol that I'm using for area. So we're going to relabel that C. Okay, so now we can plug that into here. Okay, let's see what we get out of that. So we're going to integrate over our solid disk, r squared. Now times dm is c times r to the n dA. Okay, this is better. C is a constant. And now this radius and this radius are the same thing, so distance from the origin. In other words, we're considering it about... So this was implied. Maybe I should have said this from the very beginning. Find the moment of inertia about the center. About the center of mass. Right at the center. So we're computing it about that central part. So it's implied if they don't specify a different axis that it's about the center mass. And if this was 3D, you would have to be a little bit more careful about what the axis is. But here it's implied the axis is perpendicular to the plane of the object. So all that's to say that this r is the same for these two, so that's great. But now how are we going to parameterize the area? So you'll notice that sigma is a function only of r. And so what you want to do is you want to split up the disk into a bunch of little rings where the ring is at some radius r, so lowercase r, and then this has thickness dr. So the area of this thing is dA equals the circumference times dr. Okay, so this will be 2 pi r dr. And if I plug that into here, so dA is 2 pi r dr. So now we're going to integrate over the disk. Actually, we can take out c at this point, and then we have r to the 2 plus n, and then dA is 2 pi r dr. So taking out a factor of 2 pi, it looks like we have 2 pi c integral of r to the n plus 3 dr. And now that we actually have something we can integrate over, we can specify the limits of integration are r equals 0, lowercase r equals 0 to capital R. Okay, so our moment of inertia is 2 pi c. Looks like it's r to the n plus 4 over 4. Okay, I equals, looks like pi times c over 2 r to the n plus 4. Now, that's not our final answer, because we don't know the constant c. So what we're allowed to use in our answer are the mass and the radius. So you might have been just told at the beginning of the problem that this is proportional to r to the n, and you're not told what that constant was. In which case that really means that you have to write your answer in terms of r and m right here. So let's see, how can we solve for c? How can we solve for c? Well, what you can do is you can set up this integral again, but just solve for the mass by not integrating r squared dm, but just integrating dm. So in other words, the total mass of the disk, which we are allowed to use in our answer, is the integral of dm over the disk. And this, so it looks like dm was equal to sigma dA, and sigma was c times r to the n. So in other words, this is c r to the n times dA over the disk. And again, we're going to use, we're splitting up our disk into a bunch of rings of area 2 pi r dr. So it looks like this is 2 pi c integral of r to the n plus 1. So that becomes 2 pi c r to the n plus 2 over n plus 2. I think I messed up right here. This should be n plus 4. Yeah, that should be n plus 4. And then, yeah, I guess we can't really simplify it beyond that, right? 2 pi c over n plus 4 r to the n plus 4. Okay, sorry about that. Okay, so this is the mass, and so we can solve for c. Looks like if we move everything over the other side, we have mass times n plus 2 over 2 pi r to the n plus 2. This equals our constant. And we are going to plug that in to right here. Okay, so plugging that in, we get I was 2 pi over n plus 4 times our constant. So that's m times n plus 2 over 2 pi r to the n plus 2, r to the n plus 4. Whew, it's getting a little algebraically intensive, right? Let's try and clean this up a bit. The 2 pi's cancel. Looks like we have m n plus 2 over n plus 4. And then r to the n plus 4 divided by r to the n plus 2 just gives you an r squared. So this is nice because it's dimensionally this makes sense. So this is just some number times mr squared. Okay, so all moments of inertia look like this. It's just some number times mr squared. So this is good. And remember, we wanted to double check that when n equals 0, we should get the result from the textbook. So when n equals 0, we get I is 2/4 or 1/2 mr squared. So that's good. That's the moment of inertia of a solid disk where the mass is spread out uniformly. Okay, so that's one double check. Another double check is the n goes to infinity limit. So if n approaches infinity, then that means the surface mass density increases the more you get to the edge. And in the limit that n goes to infinity, basically all of the mass is at the edge. So before I even plug anything in, I would expect that in the limiting case that n goes to infinity, our moment of inertia should be mr squared because all of the mass is at a distance r from our central axis. So let's double check that also. So we're going to double check n goes to infinity. So the limit as n goes to infinity of I sub n, looks like this is mr squared. And that makes sense because all of the mass should be at the edge. Okay. So this is a really powerful tool, and you're going to do this more in electricity and magnetism. You're going to take charge distributions and split them up this way. So this isn't the last time you're going to see this thing. So we did a disk. Your book also talks about doing this for a rod. So doing a rod about the center. So with the axis at the center, you would integrate from minus the length over 2 to plus length over 2. And then you get 1/12 ml squared. You could redo that integral from 0 to L, and you would get 1/3 ml squared. So you can get the two cases of like a 1D rod with mass spread out uniformly over the length of the rod. And yeah, your book does the special case of like a solid disk, but uniformly spread out. So we left it a little more general. We did a more general problem than your book does, just to show you how that works out. Your book also talks about, it mentions the parallel axis theorem, which actually will prove next chapter. So maybe I'll wait until next chapter to talk about that. Yeah, great.